So, good afternoon, everybody. It's a great pleasure to be here and being invited by Professor Boku. And I see a lot of familiar faces here. We have been seeing many people, all of you at different places. I have been to Kuba area a few times. I think once at the IEEE cluster. I don't remember the year. I think 2020. 2009 or 10. I was there. Yes, T2K system. I remember the IEEE cluster was there. My flight got cancelled and I had to give the keynote talk. Professor Boku actually drove to Narita airport to pick me. And then I just came and then gave the talk. That was the last session.
Just 1 hour before his talk.
Yeah.
To the venue, not the airport.
Yeah. So, but this time it is not like that. I came for the ISCA conference, which is taking place in Tokyo, as many of you know. So I had talked to Professor Boku. He said, why don't we come here? So it's a great pleasure, again, to come and share some of the things, what we are doing here. So as the title says, the focus will be to how to design high performance and scalable middleware, both for the HPC as well as AI. So that will be the kind of the focus here. So if you take a very broad look, go back in the history, like almost 50 years back, this scientific computing started, like 1975. And then in another 20 years, the big data analytics came. So computation was there, data was there, and people wanted to make a lot of analysis out of it. Then in another 10 years, the whole field of AI started coming. And we are living in that era with all large language models, ChatGPT, all those things are happening where we have computation, data, and also AI. But what is also happening, there is a new thing which is coming called computing continuum. Okay. So if you take a look at the left-hand side, that is like the traditional, like we have a HPC center here, you do scientific computing, big data, and AI, you have the data which is locally available. But gradually what is happening with all the advances in distributed computing, sensor technologies, IoTs, data is no longer centralized. Data can now come from a drone. It can come from some IoT devices. So, but still in those kind of applications, we need to make sure that we are also trying to apply our HPC, AI, big data kind of thing. So that is where is the challenge. How do we design this kind of software systems in that computing continuum? One such example, I'll just motivate this example, but I'll go more into details, which we have been working on our Icicle Institute. I'll go into more details. Think of like agriculture. The world is totally, these days, the population has increased. There is always a big demand to produce food with the lowest cost. Okay? So the question is, okay, traditionally, like the farmers have used their traditional knowledge, traditional technologies to harvest crops, but can we even go further? So let's say you have a big farm, and in that big farm, there are, let's say, different parts of the field get different kinds of diseases. So how quickly we can detect? Can we actually use AI technology there? Can we fly a drone? Drone takes the images. We take the image, we build an AI model for that crop and that disease. And once we build that, then again, we fly the drone with that model. And in real time, it can actually do those analysis and tell exactly which part of the field has what kind of disease. And not only we can do that, we can feed that information to even intelligent tractors so that the tractors can actually go and do very precise spraying of pesticides. Okay, it is just like, precision medicine, we can do precision. So this is where kind of the people have been thinking. Okay, so we need to solve this problem from the traditional scientific computing, AI, big data to the computing continuum. So that's how my talk will focus on. So if you take a look at in this context, of course, these are the three pillars. HPC, in the AI, we have deep learning, machine learning, and then the big data. And the question is, can we have some kind of a software which is converged software stack. I'll go into more details. Instead of using like 10 different software stacks, can we use actually one kind of stack? Because irrespective of which applications like HPC, AI, or big data, all of them need scale up and scale out. Okay, so as you know, the systems are in the scale up, like we keep on adding more number of CPUs, GPUs to a server node. So we want to get the best performance, but that is not sufficient, and we want to scale to a large number of nodes. So this is where I'll be trying to motivate, and what we have recently done is actually everything we are trying to converge over MPI. Okay, I'll actually show you some of the results and all on that system. So the broad challenge is how do we design this high performance and scalable middleware while taking advantage of the heterogeneous resources? And when I say heterogeneous, we have CPU, GPU, even DPU, as many of you know, like a Bluefield kind of devices from NVIDIA. And while we are trying to design this kind of software stack, of course, we need faster execution, higher throughput, reduced energy consumption. But at the same time here, I'll be focusing, especially since we are from an university, we are trying to provide a solution which is vendor neutral. Okay, so the stack will actually run on any combination of CPU, GPU, interconnect. So we are not like saying, okay, it will only run on this vendor's hardware or that vendor's hardware, but vendor neutral. And that actually helps the end users and organizations, HPC centers, to have better capacity planning. And of course, the end goal is to reduce the total cost of the ownership or the TCO. So I'll have this kind of a 4 different parts I'll cover. I'll start with the MPI MPI library project. Many of you might be knowing. I'll go into more details. And then on top of that, I'll try to show you how you can build your AI framework. Okay. And due to lack of time, I'll not go into the big data, but the same things we have done. In fact, here I'll show you in this section, you can run distributed PyTorch over MPI. We have also done Spark running over MPI, Dask running over MPI, but I'll not have time to go over that. But then I'll also introduce kind of this computing continuum. As Professor Vuku introduced, I'm the overall director of this new NSF AI Institute. I'll go into a little bit more details and show you how we are developing the solutions. And I'll also touch a little bit like from the university side, we have been doing a lot of work, but we also have a lot of some of the commercial solutions. And through those commercial solutions, with a startup, we are actually working with a lot of HPC centers all over the world to really give much more benefit to those organizations. So within MPI's library, I'll start with a very broad overview, go into this converged software stack, what we are planning to do. I'll show you some sample performance numbers on leading systems. And then I'll introduce 2 of the new things recently we are working on is called the on-the-fly compression with GPU. Basically like using to accelerate communication while trying to do an on-the-fly compression. And I'll also try to show how we are trying to offload internal MPI functionalities to the DPUs. Okay, just to go into a little bit more depth, and then I'll talk about the broader impact and then go into the other sections. So this is how many of you know MPI's project? Many of you. So in fact, we started this project as soon as InfiniBand was introduced. I'm sure all of you know about InfiniBand. It was introduced in October 2000, 25 years back. Okay. Prior to that, my group was working on Myrinet, Quadrix. Those were the older interconnects. But when InfiniBand came, we were the very first one in the world to really have an MPI, open source MPI, and we demonstrated it at Supercomputing 2002 in Baltimore. Okay, and that time it was very hard even to have a demo with only 8 nodes of InfiniBand. Okay, but now you see over 25 years, people are deploying 8,000 nodes of InfiniBand in a much more reliable manner. So I'm very proud of my team who have been working in this area. Now, of course, we started with InfiniBand, but now the MPI's library supports all interconnects. You name any interconnects, it supports. We also have, many of you might be knowing, we have the OSU MPI micro benchmarks. And of course, over the years, we have introduced also a lot of specialized version of MPI, like MPI to GDR, MPI to X, MPI to over KNL. So a lot of things we have done as the technology evolves, we have optimized designs. And as Professor Boku introduced, like currently these libraries are being used by more than 3,450 organizations. If you go to the listed on the user tabs of the MAPICH page, you will see those organizations. Many of them are in Japan. And we are almost heading into 2 million downloads just from our website. Of course, we are a part of like Red Hat, SUSE, OpenHPC, SPAC. We can't keep track of those, so we just keep track of like the downloads from our website. And of course, it is empowering a lot of top 500 clusters. So you can see very quick kind of a reflection on the total number of downloads over the years and how it is increasing. But this is the overall like the architecture of the MAPICH MPI library. If you take a look at the left-hand side, these are all the different networking technologies and their features. And then these are all the CPU, GPU, DPUs. So every time a new technology comes, this becomes the biggest or open problems for my students and staff to see how to optimize those. Okay. And then, so these are the, of course, the inside the MPI library, as many of you know, like the point-to-point, collective, startup, energy awareness. So these are the actually our publications we come up with. And once we publish these papers, in 6 to 9 months, within my group, we have a software engineering team who actually takes, and the students work very close with those software engineers to really bring it into the actual the release point of view. And in the earlier days, we started with MPI, but then in the 2000, we also expanded to PGAS. That time it was a very hot topic: PGAS, hybrid MPI, PGAS, MPIX. So we have all those supports. But now what we are trying to do is, in addition to this HPC, we have also expanded to AI, deep learning, machine learning, big data, and data science. So the idea is like this. So if you think of like especially HPC and MPI libraries, every time a new technology comes, whether it is a CPU, GPU, GPU, interconnect, MPI technology is always the very first one to embrace it, and then trying to see, okay, how we can take advantage of that. Okay, for communication, both scale up and scale out. So now, since we have that layer, the question is, can we actually have AI workload running on top of it? Okay. Similarly, can we run also big data and data science? So then what happens, we don't have to redesign those libraries again. Whatever we have done in the MPI, if we can leverage that, even your PyTorch can use it, Dask can use it, Spark can use it, but we need to provide the appropriate stack. And that's what we have been working for the last several years. And to provide the scaling and performance portability across any combinations of CPU, GPU, interconnect. And this is what is the vendor neutrality. Okay, so if you take a look at like a current, just for an example, like let's say 3 kinds of CPUs: Intel x86, Intel AMD, and ARM. Okay, let's say 3 CPUs. Let's assume 4 interconnect: InfiniBand, Rocky, Cray Slingshot, and Omnipath networks. And then GPUs again 2 or 3, like a NVIDIA, AMD, and Intel. So if you do a quick math, 36 combinations are there. Okay. So from an end user perspective, if you are an HPC center manager, you have complete freedom to choose based on your budget the CPU, GPU, and the interconnect. But then the question is, who will provide the software stack? Okay. So for example, if you go to NVIDIA, again, I'm just giving some examples. I don't want to offend anybody. NVIDIA will say, okay, if you are buying ARM CPU, NVIDIA GPU, InfiniBand, I'll give you the stack. Okay. But if like a few years back, I think 2 years back, if you remember, like the UK Bristol, the system called Isambard, some of you must have heard of. That system actually has the ARM CPU, NVIDIA GPU, but a Cray Slingshot. So if you go and talk to them, in the beginning, NVIDIA didn't even want to recognize that that is their system, okay, because InfiniBand was not there. But then the question is, like, who provides the software stack? Cray HP was the vendor. They provided the Cray pitch. But then the question is Cray pitch optimized for that system or not? So like this, a lot of these different combinations are coming. Now, if you may buy your hardware, but then if the software stack is not optimized, you are not harnessing the full potential. So this is where, from an MAPICH project perspective, we are trying to make sure that we provide this kind of support, and I'll show you concrete numbers, okay? Saying that MAPIC, you download, you use it, you will get the best performance on all these different kinds of platforms, okay? Irrespective of any combination. And at the same time, we're also trying to address the cloud so that we have also solution for AWS, Azure, Oracle, all the cloud providers. So this is our latest release. So earlier, as I told, some of you might be remembering, when we started like a GPU, things came, GPU direct RDMA. We from OSU collaborated with Mellanox that time, which was not part of NVIDIA and NVIDIA, to have a GPU direct RDMA. So we had a new library called MAPIC to GDR. Then later on, we had an MAPIC to X. So like this, a lot of versions were there. So the community got a little bit confused. They gave us feedback saying that, can we actually bring down the number of versions? And that's what we have done recently. So recently, if you go to our MAPIC site, there are only 2 versions, okay? There is a basic MAPIC, then the other one we call MAPIC Plus, that's all, okay? So the older versions are being folded into. The MAPIC Plus now has all those GPU direct RDMA functionalities, support for all the GPU, all those features have been combined. So this is our latest release. We made few I think, before ISC, like 2 weeks back. So if you are on our mailing list, you would have seen an announcement. So here what we do is, as you know, like this interconnect community, many years back, it used to be only the open fabrics. But now they have got split. So there is a UCX camp, there is a Wi-Fi camp. So we again try to remain vendor neutral. We support both of them, Wi-Fi and UCX. So depending on which interconnect you want to use, like if you have an InfiniBand interconnect, configure our MAPIC Plus with UCX. If you have a Cray Slingshot, you configure MAPIC Plus with Wi-Fi. So like this, we support all the different devices. And that's what, like all these combinations, I showed you like those 36 combinations we support. You can download and they're optimized for all these 36 combinations. And then below, inside, we have all the support for CUDA-aware MPI, on-the-fly compression. I'll go into more details. So what we call like this is a base package. Think of like a base package. On top of this is our converged software stack, okay? So you have the base package, which is for HPC, but then we have another project like an MPI DL, okay? MPI for QML. So I'll go into some of these. So you think of like these are plugin packages. So this will run on top of MPI for AI workload, big data workload. So depending on your need, you can actually download those, and it's a converged ecosystem. And in fact, through that, I'll show you, for example, all these AI workload, as you know, the vendors are coming up with their collective communication library. Like you go to NVIDIA, they will say, okay, use only Nickel. Go to AMD, they will say Rickel. Go to Intel, they will say XCCL. In fact, you don't need any of those libraries. I'll show you, without all those things, pure MPI, MAPIC supports all the collective operations, okay? And I'll show you the numbers, they're equal or better compared to all those Nickel, Rickel, okay? So, so in addition to the basic MPI, we also have this OSU micro benchmarks. As some of you know, we started this project almost like in 2004. And continuously, every time we have a newer feature, we also add the corresponding OMB, okay? So that you can actually go and reproduce those kind of numbers. So let's take a look at some of the sample numbers. I chose 3 systems. So this is what like a frontier, as some of you know, like it used to be number 1 earlier, now it is number 4. It has AMD CPU, AMD GPU Slingshot. The second one is the Vista at Texas Advanced Computing Center. It has the Grasshopper and InfiniBand. This is very similar to your Miyabi system in this building. So then recently, you must have heard of AMD coming up with this APU architecture, not the GPU, but APU. So this is a system has been deployed at San Diego Supercomputer Center, APU and Slingshot. So I'll show you that our latest release, actually, irrespective of any of this combination, it gives the best performance, okay? So let's take a look at one by one. So this is the frontier system. The Cray MPG is the default because it was, the vendor is Cray API. So what we are trying to show here, the basic OMB numbers, like this is latency, lower is better. These are the unidirectional bandwidth, higher is better. These are the bidirectional bandwidth, higher is better. So as you can see, compared to a vendor proprietary library, Cray MPG, we are able to compete our MAPIC Plus and delivers better performance. So that is like an intra-node. This is inter-node. So inter-node, again, we use OFI stack. OFI, because the Cray hardware, like the Cray Slingshot, doesn't give the lowest API available to the users. They only go through OFI. So we are calling it, Cray MPH also calling it. So more or less, you will see very similar kind of things. But at some levels, you can still see, like our bandwidth, we are able to deliver better bandwidth and better high-definition bandwidth. These are the collectives. As you know, the collectives are becoming very important, not only for HPC, but for all the AI work. Okay, so you go to any training, inferencing, this is where like all reduce, all to all, reduce scatter, all gather. These are GPU-based collectives are becoming very important. So here you can see on this frontier, so what I'm trying to show, these are all the 128 GPUs, and they're divided into through these, the message sizes, small, medium, and then the large message. And what we are comparing, like not only Cray and pitch, but as I was telling earlier, for all these AI workload, AMD is saying, okay, you use our Recall library. Okay, it's equivalent to like the Nickel library for NVIDIA. And as you can see, for small messages, like here we deliver very good performance compared to MPH. Cray MPH, medium, again, we are always the best. And as you can see, the Recall is also not delivering very good performance here. And if you have very large messages, you see the MPH Plus is delivering the best performance.
Why can delivery so bad?
Which one?
Our CCL is performance good.
Which one?
Original Recall.
Recall.
Yeah. What is the reason why Rico is very slow?
You need to ask to AMD. That's all. You need to ask. So that's what the numbers we are like. We are running whatever is the very latest one, whatever is the thing. You see, all these layers need to be optimized. That's what I'm telling. Okay. So the AI community is rediscovering those collectives. Okay. But MPI, as you know, the community has been optimizing these collectives for many years. So, so then let's take a look at the next system, which is like the tag vista is similar to Miyabi system. So this is again the same all reduce. So here it is what we compared this is the tag vista system. So there are 4 of these. We have the MPH Plus. There are 2 again Nickel, as you know, they're coming up with continuously near better versions. So there is a system installed version that is the 2.19.3, then 2.21.5, which was like a released few weeks back. So we took both of them. And also it is an NVIDIA system, so it's an open API. So we are comparing with 4. So once again, you will see like MPH Plus is delivering the best performance for small messages, medium messages, and also large messages. And here again, you see OpenMPI is just shooting up like anything. It's not optimized here at all. Okay, but here we are able to exactly match with even whatever the Nickel is doing. So then that is like all reduce. Here it is an all gather. Very similar story. Here we are trying to OpenMPI actually is delivering better than us. So we need to still see whether we can optimize this even better. That is for like a small messages, but large messages, as you can see, we are able to even deliver good performance except like this message size. Okay. So, reduce scatter, that is also another collective which is being used in the AI. The very similar story. Here you will see the Nickels are very high, and even this MPH Plus. We are trying to give very similar to OpenMPI. So like this, you will see what I'm trying to say is like in the end, if there is a vendor software stack, they need to actually optimize. If not, you can always download MPH Plus and then see the best performance. Okay. So this is actually an application. So this is the WRF, which is the weather forecasting model, as you know. So here we ran with like this is a pure CPU run. 32 nodes with 144 ppm. This is the Grace Hopper system. And as you can see, as the system size is increasing, we are able to, MPH Plus is trying to sign like around like a 32 nodes, 144. So there's like a 5,000 core experiments. We are able to give even better than even OpenMPI around 5%. So then this is the system, the APU. So this is the APU architecture is very new. You will see very soon people will be coming. This the compared to the traditional CPU and GPU where your memory, you have to move data from CPU memory to GPU memory, whereas here CPU and GPUs are sharing the same memory. So you can actually, there are a lot of opportunities here to optimize all this communication stack. Okay, and that's what we have done. So these are the very early experience. This system was just deployed just a few weeks back, we got access to the early users. So here, again, this is because it's a Cray slingshot system, it's the Cray is there. So here you can see like these are the basic latency numbers. So this is like the all reduce. And let me try to move this. And here you can see like as a large message sizes, we are able to give very good performance. So similarly here, like this is the, again on the same system for the other collectives, you can see like for small messages, almost 82%, 32% kind of things, we are able to give benefits. This is also the very similar story again. So compared to again, vendors supplied stack, we are able to deliver good performance. And these are some application numbers. So again, the open form, here we ran like these are the CPU experiments. We are able to see as the number of nodes are increasing, we are getting around like a 6% better. And in fact, when we ran WRAF, even the Cray MPs doesn't run on this system. There are errors and all, so you cannot run. So the vendors are just giving the systems, but they are not optimizing, okay, or not making sure that these things are running. Whereas from an MFPs Plus side, we make sure that these things are running and give it to the release. So those are just like a sample numbers, but we can have, I mean, you can download if you have any different configuration, please feel free to run. If you don't see good performance, let us know. And then we can work with you to see how to optimize it further. So with this, let me go into this some new, little bit more design details into things, the on-the-fly compression. I think this is the work we have been doing for the last 3 years. So always GPUs, people have used for computation. But the question is, if you are shedding large data, what we started this work saying, can we, instead of blindly sending, like let's say 8 gigabytes of data, can we use the GPU to compress? Okay. Of course, compression will have some overhead. But if the compression is effective, again, it is dependent on the data, dependent on the application. If it's successful, in addition to the overhead of compressing and then the decompressing, because the message size will reduce, we may win. That is the whole idea. Okay. So that's why we call the on the fly. So like actually API calls takes place, and in that point-to-point or collectives, below there we are trying to do this compression, and we have like a lossless compression, lossy compression. We are trying to make those modular so that you can also use your own compression algorithm there if you design. So what you will see here is very interesting trend. So let's say this is the middle line. So this is like the our MHAPich numbers, OpenMPI, they are very similar. But now if I start using compression, you see there are like a different compression rate 8, compression rate 4. These are like a parameters, runtime parameters. You can choose, and you see your latency is reducing. Okay, so that is the kind of the benefit what we see. Even though you pay overhead on the sender and receiver, but you are still able to get the overall benefits. And this is actually the number on the frontier system. So we have a point-to-point compression. We also have collective compression. Okay, and collective is like a all-to-all on frontier. So here you will see like a. So this is what like a, let's say the MFPich plus the default, that is the black line. And then with the GFP8, you see, we can actually improve. And again, this all-to-all, we can use in some of the collectives, the AI workload, compared to a Recall, you will see very higher benefits, you see. So this was also another study we did. This was the very original paper we started. This was the best paper finalist at IPDBase in May 2021. So we worked with the AWP ODC. This is a seismic simulation group at the San Diego Supercomputer Center. So they actually have this model which simulates the earthquake behavior in California. Okay. So here, if you see, so we have, these are the different schemes. So what we are trying to do, like at the application level. Okay. So you can always say like sometimes in the compression, again, it is based on data characteristics. If the question is whether it is still that your application is converging or not, even though I do the compression. So here we validated AWODC was running, giving the exact same results. So accuracy, everything is the same. But here we are seeing like the left-hand side is like a GPU computing flops. Higher is better. From the same hardware, we are able to give you even better performance, like 18%, 35% higher performance. And the right-hand side is the latency. runtime per time step, we are reducing by 26%, 15%. Okay. So it is exactly the same hardware, but through MRPs Plus, we are giving you some newer capabilities so that you can actually, your applications can run better. So that is the on-the-fly compression, the DPUs. How many of you are familiar with the DPUs, like a Bluefield 2? Okay. So if you take a look at this, these are like the traditionally, let's say this was the InfiniBand NIC. Now this NIC has also a set of ARM cores. Okay. So here 16 ARM cores, and these are the CPUs. I call it like a executive assistant. So think of like in a organization, I'm sure some of you are managers. You have assistants and secretaries to help you. So we are taking the same executive assistant paradigm and trying to see how we can reorganize MPI internals. Okay. So what portion of the MPI and also some of the more advanced designs, I'll try to show you. So this actually is being done. Some research has taken place from the OSU side, but is also the actual product is available from this startup. I'll go into a little bit more details. The company side, Xtep Solutions. So a lot of these things, like we have taken like a non-blocking collectives, all-to-all, even non-blocking point-to-point, IB cast. These are some of the results. So one thing to note, when you are trying to do offload, let's say with a non-blocking collectives, your application may need to be modified. If you don't modify the application, you may not see the benefit. Like I cannot take an application with a blocking all-to-all and then just change to non-blocking all-to-all and expect benefits. So the idea here is that just like executive secretaries, you tell your secretaries to work on something, but you are not just sitting idle. You are trying to do your computation. So that means you have to modify your workflow so that you do some computation, do the non-blocking collectives, and then bring back. While the communication is happening, you can actually do more computation so that you can get this overlap of computation. That is the whole idea. So here we actually worked this P3D FFT from San Diego, University of California. So we worked with them, they modified the things and we evaluated. So now you can see, this is like the basic MRPH 2, this is the MRPH 2 DPU at an application level. Here you can see from the same hardware, we can give you benefits like 17%, 16%, depending on the grid size and all. Okay. The right-hand side is trying to show, so this is with all-to-all, non-blocking. The right-hand side is like a non-blocking bcast. And as many of you know, like the high-performance link pack, HPL, uses actually the bcast, non-blocking bcast. So we are able to even accelerate the HPL here. As you can see, like a 9%, 15%, 17%. So that is like an MPI offload. So recently for the last 2 years, we are working like even the PGAS offload. So these are like the one-sided operations, open SMEM, the non-blocking RMA, as you can see, like a pure host. And if you offload this paper, we presented at HPC 2024. As you can see, even with the Bluefield 3, we can get far better performance. And then finally, we have started working on offloading computation. Okay, but this is a little bit tricky in the sense these Bluefield ARM cores are not very fast compared to the CPU. So you need to do it in a very intelligent manner. If you just do blindly offload, everything will run slow. So what we have done, like we have gone into like a PETC, Hyper, those are like the kernels, scientific kernels. And inside that, they have vector multiplier, distributed dot, matrix vector. So within that, we have tried to see what you can do with ARM, what you can do with the CPUs. And then your results may differ depending on, like whether I'm using an older CPU plus Bluefield 3 or a newer CPU with Bluefield 3, because the relative performance of the host and assistant matters. Just like what we see in the real world, right? If you are a manager and if you are not very efficient, your secretary can do things faster. Okay? But if you are a very smart guy, you don't have to offload to your secretary. You can do it yourself. Okay, so that is the kind of the exploration what we are trying to do. So given based on your system, host speed and ARM core speed, we should be able to intelligently offload. And here we see like around 10 to 15% improvement with the very latest, like Intel Sapphire Rapid system and Bluefield 3. Okay? So just to highlight, so these are like some of the samples. I will not have time to go into all the designs, but just to give you like a very broader impact, as as I indicated, this project has been running for 25 years. I'm very proud of my team, students, staff. But over the years, we are seeing this kind of impact. So this is actually a statistics. I'll introduce later on. Some of you know we do an annual MHPC user group conference. So this was presented by from Idaho National Lab. Okay, this is not our data. Idaho National Lab, they are also one of the largest MHPC users. So what they said, this was their data from 2021. So their users were using all different libraries, MHPC, OpenMPI, Intel MPI. But starting 2022, as you can see, most of their users have moved to MHPC. Okay, because MHPC is able to deliver better performance for them. We also work very closely with Lawrence Livermore National Lab. They are also the very largest users of MHPC. And so we are working with them both from the OSU research side, as well as I'll introduce this company side. So through this, we are able to really work with them in a very tight manner and really help them in some of their bigger mission. Okay, because they are scientists, let's say Lawrence Livermore has 4,000 scientists. All of them are running MHPC. If some issues happen in the code or in the library, they don't want to waste time. So this is where we are able to give very rapid help to them so that their mission can proceed. So that's what happened. A few years back, you would have seen a NASA's DART mission. The NASA flew did a simulation if an asteroid comes, how it can go and attack. So we actually helped them in that. We also did a nuclear fusion research. That was the end of the 2022. So like this, we not only just give the software, but we also work with a lot of end organization and the end scientists to make sure their applications are really getting benefit. So with that, let me move quickly into the other parts, that is the pure MPI. So then this AI workload, as I said, we have a lot of the base module, which is the MHPC Plus. Then we have all these other plugins. And what we have done, I'll try to show you how you can use the same MPI library for distributed training. I'll talk a little bit about that. Then there are some research work here we'll see for training and inference. So what we have done, in fact, if you go to this high DL, we have a project called high performance DL. Okay. So typically, those of you who are familiar, the workload, let's say these days, PyTorch is very common. So below that, we have Torch distributed or even Microsoft DeepSpeed. So typically below this, if you go to NVIDIA stack, they link it to Nickel, or AMD links it to the Nickel. So instead of that, those collective communication library, we have linked to MHPC. Okay. So that as an end user, if you are running your training or inferencing, you don't have to worry anything. Your application remains unchanged. Okay. But it's the communication substrate, instead of going through Nickel or Nickel, it will go through API. Okay. And in fact, we have opened up. In fact, we were trying to make the release yesterday. Some people are still working on it. Might be tomorrow you'll see an announcement. So go to this GitHub. We have the latest version of PyTorch with our MPI link. You don't have to even do anything. You just download that, download our MHPC Plus, build it, and then it will run. Okay. So that's how we are trying to enable the community and see these numbers. So these numbers are on Vista, tag Vista, which is very similar to your Miyabi system. And what we are comparing with the Nickel run and our MHPC Plus. Okay. So the MHPC Plus, as I said, it just purely depends on MPI collective performance I showed already. Okay. So it doesn't need any Nickel. As you can see, they're exactly same performance we are able to give up to 64 GPUs. So there is no need for that kind of a Nickel library. So this is where we are trying to bring that vendor neutrality, so that if you have MHPC Plus, you can run it on this system. This is the Slingshot system, Frontier. So in fact, Frontier, earlier you saw Recall was not good. So in fact, as the system size increases, you see, we took numbers up to 128 GPUs. We can run 12% faster compared to even the Recall, whatever is installed there. This is on the HDSC MI300A system, the APU. We are able to give very similar kind of performance. So like this, not only we are trying to provide vendor neutrality, earlier I showed for HPC, but for the AI workload, we are trying to provide. So then for your deployments as an end organization, you are totally free to choose any combination of CPUs if you interconnect you don't get constrained with a vendor's cost or vendor's constraints. So through this process, we are trying to democratize the HPC and AI. So then this is some very quickly as you know, like a very context language models. How do you do the training? There are a lot of challenges are coming up. This is a paper we just presented at MLCs just 2 months back. This is a joint work we are trying to do with the DeepSpeed Microsoft. I'll not go into very details, but in the end, here the results, as you can see, like these are the results. This is not with MPI yet. This is still we are doing with nickel, and we'll move it to the MPI. So here we are able to increase the sequence length by almost 8x and keep the hardware at its highest utilization. Okay. So a lot of these LLMs, through the training, as you might have seen, the GPU utilization is very low. Okay. So people are trying to come up with better and better solutions so that the utilization remains high, and that's what we have done here. Similarly, we are working on parallel inferencing. In fact, as the training for the last several years, there was a lot of focus on training. Now, in fact, there's a lot of focus on inferencing. So here again, as you can think, like I'm sure all of you have done sometimes ChatGPT and all, right? Now, if you think of the ChatGPT server on the other end, so many requests are coming. How do I schedule them? Okay, so that everybody is getting the best performance out of it. Like the round trip time is better. So here we propose something called a proposed temporal fusion. And in fact, this is available as a release. We have made also the release. And here if you see, like compared to, like say, this is like a GPT 6 billion, Llama 13 billion, Llama 33, 65 billion. We are able to give you almost like a 16x speed down. Okay, in the inferencing compared to like what other people can give. So in fact, what happened, this was a 2023 paper. As soon as we published the paper, NVIDIA team contacted us. And again, beginning said, no, you are not running the experiments correctly. We said, no, we are running correctly. Then finally what happened is they took our design. Okay. And what you see in the very latest Tensor LT inferencing, this design is actually incorporated. Okay. So with that kind of a background, let me move it a little bit into the Icicle Institute, and then I'll try to wind down. So this is what this computing continuum I was talking. Okay. So all the previous work, whatever I presented, is on the left-hand side, but here they have this impact on the right-hand side. So the question is, you remember that drone example I indicated. Okay. So not only the drone, there are a lot of other applications I'll introduce. There is a big challenge. How do you do data movement and control? Okay. Let's say the drone is flying. Should I put the model there? Or can the drone hold the model or not? If not, the model has to be set into the near edge or into the cloud. So there is a lot of decision you need to make. So this is where this new NSF AI Institute I am leading. And if you take a look at this, the National Science Foundation in US, they have actually funded 27 of such institutes. Each one is for a $20 million for 5 years, but each one has very concrete objective. Okay. So our objective is to design this cyber infrastructure. There are like another institute for physics. There is another institute for AI in chemistry or AI in astronomy. But our focus, we have been funded with an Office of Advanced Cyber Infrastructure. So to think, how do you design this, the software, hardware, middleware for the next generation AI system? So this is where Icicle sits in. So we have this emerging computing continuum. I mentioned about digital agriculture as one example. But we also have a smart food set that is another area, or the animal ecology. So I'll only talk about a little bit about the agriculture. Okay? But similar things is happening. So this is a very large project. There are 16 universities, 30 faculty, 26 staffs, like coast to coast, with a lot of collaborators. Around 150 people are working here. OSU is the lead. I am the overall PI. But thanks to all of the other people who are doing a lot of this work. And in fact, not only we are working locally, we have started even some of the collaboration have extended, like there's a collaboration going with India, because the agriculture, as you know, is the same problem. But how you do it is very different. Like let's say in the US, we focus a lot on soybean or wheat, whereas in India, it is the rice, potato. The concept remains the same, but the data set changes. So the principles also change. So we are trying to see how our solution can be used by others. So this is the very high level research overall plan. And in this case also, one of the objectives is to really democratize these solutions. What do we mean? Like we want to make it much more easier for end users to use. Like the example, you remember the farmer example I said, digital agriculture. If I go and a farmer saying, yeah, you have to put a Linux cluster, you have to run PyTorch, that is too much. On the other hand, what we want to do is convert everything to like an app, okay, through conversational AI. So the farmer in the morning can say, okay, tell me, like what kind of diseases have happened in my field. Everything else will happen behind the scene, okay? So that is how we are trying to go to these communities, and might be the farmer will subscribe to this app with a $9.99 per month, but get all these other kind of benefits. So that's what is the conversational AI. There's a lot of focus, but below this, our research is taking place, and of course we do a lot of co-design. And I'll not go into very details, but we have like 150 people. They're divided into a lot of different thrusts, like foundation system AI, AI for CI, CI for AI, privacy, accountability, data integrity. Every thrust is divided into, again, sub-thrust, like a knowledge graphs, model commons, adaptive AI. Within that sub-thrust, again, there are a lot of challenges. So we have been working almost for last 4 years. And what is happening is not only we are publishing, just like the MAPIS library, as we have been making available to the community, or the PyTorch library, here, this is one of the mandate from the National Science Foundation saying, make all this software available to the community. So if you go down, link at your things, you'll see all these different components as they're coming up. Every 3 months, we make a release. Okay, so you can actually download, and you see people have started already using these packages. So I'll just give you a little bit of highlight for the digital agriculture because of the limited time. So the whole idea is that how do we take it through the entire spectrum? Okay, like crop health issues to data harvesting, preparation, HPC for ag AI, HPC for field computing continuum, and also even do the management. Okay, so these are the issues. If you go to any discipline, end user people are trying to utilize AI. So these are the challenges. How do you do data collection, labeling, training, quantization on the edge device? In this case, also aerial crop scouting, and how do you put all this together? Okay, so what we have done, we have developed this entire AI workflow. Okay, over the last 3 years, we have done a lot of discussion, not only within the team, but across the use. So data collection, processing. So like this, there are like 14 different modules are there, but the main thing what we want to focus is that this is modular and configurable. Okay, so if a researcher, like you are a researcher, let's say, for example, you are working on data labeling techniques, you don't have to use only our solution. You can plug and play. You can replace our module with your module. Okay, so that this entire workflow can actually be utilized by more and more people. Of course, some of these solutions are available. Let's say you go to Azure, or you go to AWS, they have a pipeline. Okay, they tell you, yeah, you use the pipeline, but that is a hardware pipeline. You cannot modify it. Whatever Azure gives you, you have to use it. But in this way, you can modify, and our expectation is that it will grow in a plug and play manner. So there is a short video here. Let me play. Can you hear? Nothing is coming, all right? The Zoom, can people hear? I shared the sound. I don't know how the sound system will work here.
Sharing the microphone to you.
Huh?
Before the screen sharing, you should turn.
I did that.
Okay.
Are the Zoom people able to hear? I think we'll skip. I'll send a pointer. There is actually in the YouTube. There's a video you can also play. But broadly, we have taken all these components. We have made it available, and this is available. These are actually 2 copies. One copy is running on San Diego Supercomputer Center. Another copy is running on at the Ohio Supercomputer Center. We are trying to put it on the Azure. So the principle is that we make it so easy. We call it BYOD, bring your own data. Okay, so if anybody wants to, like an agriculture field, if they want to build their model, we're not asking them, okay, give us the data, we'll build the model and give it back to you. Instead, they can actually interact with this system. Okay, and then once the model is built, either they can keep the model or they can give it to us to be used by others. So that is the kind of the arrangement we have done, so that over the years it can actually proceed. And in the end, you can actually, I motivated this. So this is the kind of the heat map you can actually get. You see, this is my colleague, Chris Stott. So we have actually, the Ohio State University has a lot of these farms, research farms. So we work with them. We actually, for large fields, it is not only a single drone. We are actually flying multiple drones. We are taking parallel processing to the drones also. So the drones, while they are flying, they are talking to each other, coordinating, saying, yeah, this drone will cover this part, that drone will cover this part. They exchange information, it comes to the edge or the cloud. And in the end, this is the kind of the information the farmer gets. We call it like a heat map. So it tells like this is a 2-color map, but it can be converted into multiple colors. So this red area says that, okay, these are the kind of the places where you have to spray. Okay, and this can actually be converted into a safe file and then given to the tractors. And these intelligent tractors these days, they have also GPUs, NVIDIA GPUs, cameras there, and they can actually go and spray it. So we are trying to create this entire pipeline. So drone can fly. Within few minutes, the tractor is following, and it can actually go and then spray it completely in the field in a very precise manner. Okay, so that is the kind of the solution what we are trying to produce. So in this context, we are also collaborating with a lot of other AI institutes, because many other AI institutes have very similar needs, like let's say in the medicine, in the transportation. So we are working with them, and gradually also we are going global. As I said, I gave one example. We are also like talking with a lot of other organizations in UK, Australia, if in Japan, if some of you have this kind of needs or working on some of these projects, we'll be very happy to have an international collaboration in this area. So finally, I'll just touch this point a little bit. I think I mentioned about this, that MHAPPC to DPU is from this commercial startup. So when we have all these things available from the OSU side, you can download, you can use. There is a mailing list. Some of you might have used. You ask question, we answer it. But a lot of organization, large-scale HPC centers, they want more dedicated support. The example I was giving, like a Lawrence Livermore National Lab, because they have like scientists, they don't want to say, okay, the scientist code is failing. They will post something on the MHAPPC, discuss, and wait for 10 days to get an answer, right? They want an immediate solution. So this is how it started actually. This startup company started to really provide this kind of commercial support. And through that, we have been providing the support into a lot of national libraries and international HPC centers. But then what happened, as we started engaging with these people, they wanted some value-added things. Okay, like, yeah, optimize here, optimize this application, or provide a monitoring, provide AI support. So like this, we are gradually expanding into a lot of value-added products together with commercial support. Okay, so these are like just like any other software products, we can actually work with integrators, we can work with and HPC centers so that their users get benefited. So please go to this Excel solutions. If some of you are interested, you can, we'll be happy to talk to you. And so for example, the AI, whatever I talked earlier, you can download from the OSU site, but this has all been taken together. One-click deployment, you should be able to go. We have a version available also in the AWS. We have provided a model. So you can actually just directly work with AWS or with your data and all, and have all this, the performance, whatever I showed you, directly you will be able to get the benefits. So that's how through all these different venues, we are trying to really help the end users, okay? Because people are hungry for getting performance, scalability, and usability or ease of use. That's what we are trying to do. So with this, let me conclude. As I started if you take a very broad look, upcoming exascale systems in cloud need to design with this holistic view, HPC, big data, AI, data science. This is what we are doing. Many years back, we were only the MPI group, but now we have expanded, as you can see. with a lot of these big focus. So we are continuously going into the bigger domain. I also want to highlight this little bit. As I said, some of you know, I'm happy User Group Conference. Professor Boku came as a keynote speaker, I think 3 years back, I believe. So we have this event coming up August. So this time we have a very impressive list of speakers already. Dan Stangioni from Meta. These are keynote speakers. We have a lot of speakers from all over the world. And we do this. We also have a lot of sponsors this time, Broadcom and Fabrica, Keysight, NVIDIA, Paratools. So this will be done in a hybrid manner, and online registration is free. So anybody can register. Please feel free to go to the site. It's a 3 days event we do. A lot of interesting talks. If you are interested, in fact, if you're interested in presenting something, let me know also. We can invite you as speaker. If you have some good numbers or good things to show with MapPage or AI and all, we'll be very happy to bring you as a speaker. So with this, I'd like to give thanks to all our sponsors. But more importantly, these are all my heroes. What I just presented within 1 hour is actually 30 years of work. And these are like my own group, HPC, AI, and big data and all. But these are all the other icicle group I talked about. That is a much more larger group. So these are the people who are doing very hard work. And every time I come to another country, I always show these slides. We are always looking for people. If you are a student listening or a postdoc, research scientist, if you'd like to come to OSU, your name will be in that previous list in a few years. Okay. So with this, I'd like to conclude here, and I'll be happy to take questions now. I think it is almost the dot, or in the later part.
Okay, thank you.
Thank you.
So it's already past almost 1 year, 1 hour, but then today we have the final part of the seminar. We also have some open question time, but if you have any short question, or especially focusing on the DK's talk, we like to take it. Okay, Nani-san, please.
Sure.
Microphone.
Yeah, I think yes.
Thank you. Thank you very much for very nice talk. I'm interested in the difference between the current or GPU cluster, current GPU cluster architecture and the traditional GPU architecture. Traditionally, we had 2 CPUs with 4 GPUs, and they are separated and distant. But nowadays, we have Grace Hopper and MI300A. These are very closely connected. So the architecture is changing. So, did Empafich made some difference for this difference, or are you going to add something for Empafich in the future?
Yeah, so that is a very good question. So in fact, what I showed some results, these are some intermediate results. We already have designs. Some papers are under review. So you will see those coming out in the pipeline. In the next, we have submitted some to the Hot Interconnect. I am hoping to get accepted. I think tomorrow or day after we'll hear. Some other are in the other conference pipelines. Because that APU architecture opens up a lot of opportunities to optimize the communication stack, data movement. So we have already started doing some of those things. And when I showed some of the MI300 results, those designs are already there in the MIPS Plus. Okay.
By the way, Fujita-san, I'm going to talk something about some on the NPI.
Yeah, yes, I will have something.
Okay.
So maybe there. This place. Okay, here. So that in the next talk by Fujita-san, we have some very preliminary evaluation of the GDR and also the system allocated memory of the GH200. So this is my personal comment to the Nami-san. So that not just the traditional or recent one, also the MI300A and GH200 has a totally different kind of the memory architecture. And we need to be very care about also that which part of the total chip is connected to the PCI Express to go to the HCA. So that is another issue. so that it is not just traditional and the new architecture.
Yeah, thank you. Thank you very much.
Sure.
Maybe I will talk day after tomorrow about Universal School as a new machine in that context. And please look at Fujita-san's next talk, the very end part of his talk. It is related to your question. Any other question? Or, oh, yes.
So thank you very much for
Maybe.
interesting talks. So that you mentioned about the data compression using GPU for the communication. And so I believe so, and also that you are developing many kinds of AI related framework with communication. And so such kind of AI workload, so that can you apply such kind of data compression for GPU?
Yeah. So that is also a very nice question. So I didn't need to go into all the details. So what we have done, the compression we enabled in the very beginning only point to point, and collectives. Collectives like you can think of all-to-all compression. That's what we have done. Within the lab, we have now also for all reduce. We also have for reduce scatter. So if you do those kind of a compression, as you know, the AI workload is trying to use all these collectives. So in fact, you will get even bigger boost. Okay. So that complete evaluation we have not done yet. But that is the direction we are heading. So not only we help HPC application, which I showed some numbers, but in the end, your AI training, AI inferencing, all those things will also get benefited.
Any other question? So if the online people, you have a question, please raise your hand. I will pick them. Or maybe we will continue the question and also the discussion in the last part of today's seminar. Okay, that is the end of the first talk. Thank you very much.
Thank you.